Good?
There we go.
We're good. Okay. All right. So, chapters 1 and 2 test on the 11th. So, everything we've covered so far and today is on that test. Okay? Everything. You guys have had homework, you've had homework quizzes, you've had study stuff. I will get you, let's see, today is Wednesday. I will get you on Monday, I will get you a study guide. Okay? So you need to do that. I'll also get a homework quiz up for today's stuff. It's going to look familiar to all those things, okay? I'm not interested in playing games with you and messing you up. It'll be pretty straightforward, but it will be comprehensive. So you've got to know your stuff. All right? Let's pray. Heavenly Father, thank you for today, for these souls that are here. Thank you for this study of chemistry, of matter. Thank you that you spoke the world into existence. You gave us life. Father, and the whole time you had a plan in your Son to reconcile all of creation to yourself and to save our souls. Father, we thank you, knowing that not only is Christ returning to set to right sin and to bring about perfection in the lives of men, but also, Lord, that all of creation, all of matter is yearning to be redeemed from the curse, to be set right. Father, we look forward to that day when you make all things new. We pray during this time that you would help us as we study matter and life, that you would help me to be just clear, or to be sensitive even to needs or a lack of understanding. Pray for each of our students that you would help us to have great focus and humility if we have questions to ask them, Lord, and give us understanding in all these things. We pray in Jesus' name. Amen. Well, all right, y'all. Let me grab this. So we were on the periodic table when last we met, right? And we had drawings of it, we talked about it, did all those kind of things. Does everybody have a copy of the periodic table?
Yes.
Get that bad boy out. Right now, I'm going to grab a new one that you don't have that's a little bit better. Phone ringing. Lightly. All right. This is a new periodic table. It's going to be a little better than your last one. You had colors. Good job on that. All right. So.
He actually has the word stuff.
Yeah. Okay. So, on the far left, where you have hydrogen, right? Okay, what are those called? Alkali metals. Just to the right of that, beginning with beryllium, what are those called?
Alkaline earth.
Alkaline earth metals, okay? Then you got this big section from scandium over to zinc. What do we call those? Transition metals. Now, y'all know that I'm not going to give you your periodic table on the test for this, right? Like, you're going to have to know this. You got to know it. Okay, then on the far right, helium, and that column going down, what do we call those?
Noble gases.
Noble gases, good. Then there's like kind of a zigzag diagonally going from boron down to astatine. What do we call those?
Metalloids.
Metalloids, good. Everything kind of above the metalloids and to the left of the noble gases. Are they metals or are they non-metals? Say non-metals, right? And we gave a funky name for that, or at least that video that we watched did. What did it call it? Shanops, right? So carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. And then, what was it, selenium?
Yes.
So it had 2 S's. So that, literally with that, oh, we got the bottom, right? What are those 2 things called? It's labeled on the new one. Lanthanide and actinide. You look at how many points you would have potentially just off of those questions, right? Okay. All right. You need to know those things. need to know periodic trends. As I move from left to right, what happens to my atomic number?
Goes up.
Goes up. What happens to my atomic mass?
Goes up.
Goes up. When I'm on the left-hand side, right, so hydrogen and down, beryllium and down, etc., etc. Actually, everything under hydrogen, how many valence shell electrons does it have?
1,
1. And under beryllium?
2,
2. And then when I get to boron, everything has 3. Carbon, 4. Nitrogen,
5,
oxygen,
6,
fluorine,
7,
and then helium has 2, but everything else in there has
8.
8. Okay, good. How many bonds would I expect to find for everything under hydrogen?
1.
1. What kind of bond will it likely make? That's a good question. It's likely to make an ionic bond. It has that 1 valence electron. Remember, it wants a full shell, so it's likely to give it away, which would then make the next shell underneath it full. So it's likely to just give that away in an ionic bond. Beryllium on down. How many bonds are they likely to make? 2. Ionic or covalent? Say ionic. Because if it can give away 2 of those, then it will have a full valence shell. Okay? Those non-metals, let me say this, let me write this, okay? When I bond a metal and a non-metal, okay?
It is ionic.
It is going to almost always be ionic, okay? All right. What else do we want to say here? And these metals, they're likely to give up their electrons, right? Because if I can get rid of them, then the lower shell will be full, it'll have a full valence. Whereas when I get over, say, to fluorine, fluorine has how many valence electrons? 7.
No,
It has 7, right? So how many more does it need to fill its valence shell?
1.
1. The electronegativity of fluorine is out of this world. It is going to just flat out take in most cases, okay? It's going to take that electron, which is going to fill its valence shell, which will make it a +1 anion, okay? All right. Let's go here. Let me grab this. There was something I wanted you to know that I didn't get you last time, and it's the periodic law, okay? I'm going to just copy this straight from the textbook. You're reading your textbook, of course. I know you are. You're all diligent students. That was a cat. So this is called the periodic law. It says, the properties of the elements are periodic functions of their atomic number. The properties of the elements are periodic functions of, like that. I have a thing with sound. Periodic functions of their atomic numbers. Whether you knew to say it like that or not, just by the study we've done of the periodic table, you've seen it. You know where the metals are. The metals on the left or the right of the periodic table?
Left.
They're on the left. The non-metals are on the
Right.
right. All the noble gases are right. And whenever their valence shell gets full, they will or won't bond anymore.
They won't.
They will not. Everything on the far left, how many bonds does it want to make?
1.
1. It's highly, highly reactive. You throw sodium in water, it goes bang, right? Okay. So these properties are periodic. They happen in regular intervals. Now there's a difference. Take a look here real quick at copper, silver, and gold. It's under 11, right? So there's copper at the top, and right below it is silver, and right below it is gold. What do copper, silver, and gold have in common?
They're in the 11th group.
Okay. What else? Just in your experience. I'm not talking like on a periodic table.
Metals.
They're metals. What else?
Conductive.
They're highly conductive. What else?
Valuable.
They have some value. They have a lot. They're lustrous. I mean, you think about silver and gold, and I guess platinum maybe more so, but those two are the metals that we use for jewelry and for coins and stuff like that. And just look at how interesting it is that they should have very similar properties. Now we know they have different colors and things like that. They're very soft, though, right? Look at how they have. They're right there in number 11. Okay. This is true for all these. So the properties of elements are periodic functions of their atomic numbers. That was the big deal about discovering that this is the periodic law, and then arranging that in a chart, we can see it, and it's really, really helpful. Okay, so I do want you to know that. We covered that. I'll give you a quiz on it. That'll help you. Let's go to ionic compounds. Okay. So you can kind of draw a line. This chapter that we're in right now kind of throws together all of the early basic things. Even if, maybe normally they'd be in a different chapter or something like that, if we were taking it slower. In a class in this setting, it's all slammed together into kind of one unit, because next unit we take off. So we're going to do ionic and molecular compounds. So I want to talk about ionic compounds in particular. Who can define an ionic compound for me? Who can define an ionic bond for me? Yes, sir.
So an ionic bond is when a metal gives up an electron or more to a non-metal.
Okay. Okay, define what's happening in the ionic bond.
The metal, since it has given up an electron, has a positive charge.
Oh, you're going too far. I want it simpler.
One element is given an electron to
Yeah.
the other.
A bond is a relationship of electrons, right? Of valence electrons. So in a covalent bond, they're sharing them. Maybe evenly, maybe not. Maybe it's polar, maybe it's nonpolar. But in an ionic bond, one's giving, one's taking, right? Which means one's going to have what charge? Positive, and one's going to have what charge?
Negative.
Negative, okay. So ionic compounds, obviously they're formed from ionic bonds, right? We're going to have one atom. I'm assuming what we call a diatomic here. Not all ionic compounds have only two, but right now we're going with it. So one atom has a positive charge, okay, and one atom has a negative charge. And we're going to talk about these. Our friend Matthew was filling us in a little bit with some extra information. Well, it's extra in the moment, but it's really necessary here. So, he said ionic bonds happen between metals and non-metals. Which one is likely to give up an electron? You may not answer. The metal is going to give it up. Look at where it's at on the periodic table, right? It's on the left. It wants to get rid of it. So, the one with a positive charge is going to be my metal. Which means this one is going to be a non-metal. Okay? And we have names for these. Okay? Positive and negative. Cation and anion. An like anti, kind of that sound, so negative. So the one that has a negative charge is my anion. And the one with a positive is my cation. You do have to know these. These vocabulary terms are not going away. You don't even know that you're doing it. I know.
I get very fishy.
Yeah, it's okay. So ionic compounds, they form from ionic bonds. One atom has a positive charge, it's going to be a metal, it's going to form a cation. One atom has a negative charge, it's a non-metal, it's going to form an anion. There are exceptions here, right? Like hydrogen. Hydrogen is going to give up an electron, and that's not a metal, right? So there are exceptions. All right, let's see what else we want to cover here. Sure.
So water is both an ionic bond and a covalent bond, because OH it is anion.
Yeah, it's right on the cusp.
And hydrogen is an ionic. It is cation, but they are also all non-metals.
Yes. All right. Far more important well, when we get to solution chemistry, for sure. Okay. Here's something to think about. Let's look at lithium. How many electrons is lithium going to give up?
One.
Why one?
The first group.
It's the first group, so it has one valence electron. That's all it wants to give up. It would take so much to strip lithium of another electron. Like, it's going to hold on to those two for dear life. But that first one, it'll give away for free. How many will beryllium give up? Two. Okay. You get into these transition metals, sometimes they'll give up 2, sometimes they'll give up 1, sometimes they'll give up 3. They get weird because there are some different rules that apply there. But certainly when we're looking at group 1 and group 2, group 1 wants to give up 1 because it's only got 1 valence shell. Group 2 wants to give up 2. They'll give up as many as it takes to complete a lower valence shell. Okay? So that's something that you do want to know there. And then on the other side of it, when you look at like fluorine, how many does fluorine want to take? 1, because it wants to fill that valence shell. How many does oxygen, how many potentially could oxygen take? 2, because it wants to fill that valence shell. Okay, let's go to the next part. I guess this is it. This is our last topic for chapter 2, okay? Draw a line. Okay. This is called nomenclature. All right? You know what? I take that back. I skipped something. We need to do polyatomic ions first. At this point, we've been working with just 2 atoms or 2 elements coming together, maybe lithium and fluorine. And so if I took lithium and I took fluorine, right? What would I get on the other side?
Lithium fluoride.
Well, kind of. I get lithium. What charge? Positive. And fluorine? The negative. But just 2 atoms there, right? That's all there is. Maybe I could do beryllium fluoride. I could do beryllium and fluorine. How many electrons does beryllium want to get rid of?
2.
Wants to get rid of 2, right? And so when I go to this other side, it's going to be plus 2. How many does fluorine want to pick up? How many fluorines do I need to match my beryllium? 2. I need 2 of them, right? I'm going to do that in a different color because that will be helpful for you. 2 fluorines, and then I'm going to get over here 2 fluorines with a negative charge, right? Notice that my charges work out. Beryllium has a plus 2 charge, right, which is what I want. Fluorine has a negative charge, but I got 2 electrons it's trying to get rid of, so I need 2 fluorines to take it. And everything balances out there and looks good. So still, I'm only working with 2 atoms, right? Even though we got more than 2, but 2 types. Now we're going to go to what's called polyatomic ions, so many atoms that form an ion. So what do we want to know about polyatomic ions? Well, first of all, there are many atoms functioning together. For instance, I could do, let's do NH4. So this is ammonium. And what this looks like is this. So nitrogen has 5 valence electrons. So you'd expect it to make 3 bonds to get to 8, which it does readily. But it's got this extra pair of electrons here. And if you get a hydrogen ion, or hydronium ion that has just the H+, it doesn't have an electron, and it gets near to this, it will form an ionic bond. And so you can get these 2 to share here, right? So I'll have a slight positive charge over here. This is an ion. This will freely dissociate. Okay? It can attach, it can detach. It can attach, it can detach. Very readily. Nitrogen likes its electrons. It's perfectly happy to hold on to them. It doesn't have any need to share with the hydrogen. This whole thing, okay, has a positive charge of 1. This is many atoms, polyatomic, and it's an ion because of this. This freely dissociates here. Okay? Another one that would be good to look at is, let's do hydroxide. OH negative, okay, it's hydroxide. Okay, the way we draw this, you'd have oxygen, right? And now, oxygen has how many protons? 8. How many its valence?
6.
6. But how many things is it saying?
80.
Let's do this. Let's count our protons. How many protons?
8.
8. So that's 9, right? Let's count our electrons. 1, 2, 3, 4, 5, 6, 7. What am I doing wrong? Sorry, my head is out of this. I don't know why.
Oxygen has 6 valence electrons.
I know. Give me 1 second. But what normally happens, say for water, is you form this, right? Everybody's content. Everything's good. Now I take away one of my hydrogens, and I keep the electron there, right? So I just took an electron, so that gives me a negative charge, which is what's happening with my hydroxide. So got myself just worked into it. Bit of a rabbit hole overthinking it. This thing has a negative charge. Okay. So these polyatomic ions, they're made up of multiple atoms instead of being an individual atom. And they have a charge, some positive, some negative. Did I hand you out a polyatomic ion sheet previously? Never got one from you? No. Okay. Give me just a second. Let me go see if I have them sitting in my office. I'll be right back. You will not have to memorize these, okay? Certain ones you'll get familiar with just by use, but I will always give you this chart, okay? All right, so this is a list of the polyatomic ions, at least the more common ones. If you put it to this side, you notice it says, you know, they're ammonium and then acetate, chlorate, chlorite, cyanate, cyanide, etc., etc., etc. It's giving you the common name of the ion, it's giving you the formula for that ion, and then it's giving you the charge of that ion, okay? Turn it over to the back side. And again, you've got your similar list here, along with just some monatomic as well, looks like. So, okay. Some rules, some things that we need to know, especially for the ones that involve oxygen. We're still under this heading of polyatomic ions. There's a specific class of polyatomic ions that involve oxygen. Let me read this to you, I believe. Okay, so oxyanions. It says oxyanions are polyatomic ions that contain one or more oxygen atoms. Note that there's a system for naming some polyatomic ions, especially the ones with oxygen here, designated by whether they have more or less oxygen atoms. So I'm going to give you 4 drawings here. I do want you to draw them kind of going across your page. This is chlorine with an oxygen, right? This is, this is chlorine with 2 oxygens, this is chlorine with 3 oxygens, this is chlorine with 4 oxygens, okay? The number of oxygens is changing each time, right? So we need a way to name this. We can't just say chlorine oxide or something like that. That doesn't work, okay? So, in this case, I have 4 different levels of oxygen. I got 1, I got 2, I got 3, I got 4, all of them bonded to an individual chlorine atom, right? I'm going to give you some Greek prefixes that you want to know here. One is hyper, and the other is hypo. You've heard of them before, right? Hyper and hypo. If your parents told you that you were hyperactive as a child, what are they trying to convey to you?
Too much energy.
Be more active. You've got too much energy. So hyper, it literally means over or more, okay? And hypo means the opposite, means under or less, okay? That matters in just a second. But first, we start with these 2 terms, ate and ite. And ate is bigger than ite, okay? You could do it this way, ate is bigger than ite. So, I want to consider these 2 first. Which one's 8, which one's ite? 8 is 3, so this becomes 8. Okay? And this one is ite. Okay? Now, What we call this is chlorate. And we call this chlorite. Okay? Now, then we've got these two others on the ends. I've got hyper and I've got hypo. So which one is less than the ate and the ite? Where should my hypo go? Should it go here or should it go here?
The first one.
It should go here. It's less than what? Is it less than chlorate or is it less than chlorite?
Chloride.
It's less than chlorate, so I call this hypochlorite. And this one I call
Hyperchlorate.
hyperchlorate. Okay. One thing here at the end, tend to leave off, not tend to, we do leave off the HY, so this just becomes perchlorate. If you write hyper, I know what you mean, okay? That is where it's coming from. So we have hypochlorite, chlorite, chlorate, and perchlorate, which just means hyperchlorate. Why those extra two letters are killing somebody, I do not know. Let's see, so we want to do any more of these? We'll stop there. We'll deal with them when we come across them. All right. Let's go into our nomenclature, okay? Do you know that word, nomenclature?
Yes.
What does it mean?
I've heard it before, I just don't know what it means.
Okay. Anybody know that word, nomenclature?
No.
In biology, binomial nomenclature. It's a naming system. Is all that means, a system of naming. How are we going to decide what to call these things? We don't just want to make up, we have certain names for things that are not that helpful, like water. Water does not tell you what water is made of, does it? No. Water doesn't tell you the chemical formula for it, does it? No. You tell some kid, well, how do I make water? They're going to go, I don't know. But water is H2O, right? How many hydrogens do I have here? Two. So we actually, you don't need to write this down. I'm just trying to give you an example of why this is useful. So I've got two, I would give it the Greek prefix di. So this is dihydrogen. And then how many oxygens do I have? One, so monoxide. Dihydrogen monoxide. They used to like put this joke around, or I don't know what it was. Talking about how many, because they tell you about how everything's killing you and you need to be afraid of everything. So there's like this article talking about dihydrogen monoxide and how it was killing, so many people a year. Some people because they ingested too much of it into their lungs. Some because they weren't getting enough of it. And so it's just talking about people drowning and people like dying of thirst. And so, it's just talking about water. It's just getting to the point, like, this is kind of silly. But this is a very specific name. This tells me a lot of information, right? Water doesn't tell me anything. If we named everything but like we do water, it'd be a hot mess. You would have no idea what anything was. But we have a system of naming. We have a nomenclature, right? So that's our word. That's what we're going to do, nomenclature. System of naming, right? And I'm going to teach you all some rules. You ready? Let's start with this. First of all, we're going to deal with ionic. I should put my nomenclature in the middle. Let's do that. Nomenclature. Okay, so system of naming. We'll go with ionic. And we're going to start here, okay? You're not writing anything.
Most of this I already know. The only thing
You
I
didn't know the word nomenclature.
The only thing I didn't know was what nomenclature meant.
Well, I hope you're as good as you think you are. Okay,
I've done naming compounds. I just didn't know what the name was.
okay. We're going to look at naming ionic compounds, okay? So, we're going to come over here and we're going to do binary ionic. So this is if I just have two atoms, okay? So the first thing I'm going to do bear with me. I had my notes written out on the ground. Change this to monoatomic. Monoatomic. Okay. The name of a binary compound containing monoatomic ions consists of the name of the cation followed by the name of the anion. It's that simple. So, I name my cation plus my anion. So, my cation, is that a metal or a non-metal? Okay, so I name my metal first. And then I add my non-metal. For example, okay, I could do, let's do beryllium fluoride. So BeF2. Right, this would be beryllium fluoride. I don't have to say beryllium difluoride here because the chemical formula and the fact that it's monoatomic, and I can look at my charges and I can know, okay, beryllium fluoride is going to have beryllium and it's going to have 2 fluorines, okay? It's going to be important in a minute. We'll practice these, okay? Do you want another example of something like this? Okay, let's do NaCl. NaCl. What would I call that?
Sodium chloride.
Sodium chloride. What is this? What is sodium chloride?
Isn't it salt?
It's just table salt. We got to be careful about the word salt. There are tons of salts. But here we specifically mean the salt that's derived from sodium and chlorine forming a crystal together. Okay? All right, so those are our monoatomics. Only 2 types of atoms. Doesn't mean there are only 2 atoms total, but 2 types of atoms. Here's beryllium fluoride. So, all right, let's go to the next one. The next one is going to be polyatomic ions. I'm going to run out of room. I already see it coming. It is what it is.
Were you probably should have done was put the ionic on that.
I should have just
board.
gone over here.
Yeah, you should have done the
It's-
ionic on that board and then the,
Yeah. Oh well. I was a little thrown because I'm like, where is that chart that I wanted? Okay, so polyatomic ions. You give the name of the metal first. Oh, I skipped a step here, guys. So you name the cation with the anion, or the metal with the non-metal, but you have to change the ending to "ide." Okay? That's a big deal that I left out. I'm going to give you a couple as an example, okay? So we can practice since I messed you up there. I do apologize for that. Okay, let's do LiCl. What is LiCl? How do I say that one?
Lithium chloride.
Lithium chloride. Okay. How do I do MgF2? What's that? Magnesium fluoride. This time I'm just going to give you two of them in a random order. You tell me what it should be, okay? You're going to have to look at your periodic table. Follow your rules. What do I list first?
calcium, bromine.
I list the metal or the non-metal first? The metal. So it's going to be calcium,
Bromine.
and then with a bromine, right? How many, by the way, how many electrons does calcium want to give up?
2.
2. How many does each bromine want to pick up?
1.
1. So how many bromines do I need?
2.
2, right? Okay, so calcium bromide, because I changed that ending to IDE. So far, so good? Okay. All right. Next one is my polyatomic. All right. On my polyatomic ions,
I don't know what that keeps happening.
I don't either, but it sure does keep up. Okay, so what I do is first, this is going to be a metal cation. I list that first. And then my polyatomic ion, or my polyatomic cation.
Okay.
Okay? So, polyatomic anion. So this one's easy, right?
There's also polyatomic cations.
Very few, but yes. Okay, so if I want to do potassium with cyanate, CNO3. I'm sorry, CNO, right? So I do K plus CNO, what am I going to name that?
Potassium cyanide.
Potassium cyanate. If I want to do beryllium, we'll do a different color. EE plus I name that
Beryllium hydroxide.
beryllium hydroxide. Just keep the name of polyatomic ion, right? I give the name of the non-metal first. You want to do a couple more? Okay, let's do it. This time, no shouting them out. Just look at them, figure them out. Try to write down the names of these so that you can see whether or not you've got it, okay? I'm gonna look on the back of here. Good. Oh no. Well, what are you gonna say here? Na. What's that? Sodium. Right. And then CO3, you just gotta look on your polyatomic ion chart there and find CO3. Flip it over to the other side. Chloride. Right, sealed. Oh, I'm sorry, CO3, not sealed. Carbonate. So this one would be just sodium carbonate. Okay. This next one, what is K? Potassium. And then Cn. Find that one on there. Okay, so this would be potassium cyanide. So everybody good here? This would be sodium carbonate. This would be potassium cyanide. This one would be, what's this? Mg?
Magnesium.
Magnesium. Then you look up ClO4. We drew it earlier. Hyperchlorate. So this would be, or perchlorate. So this would be magnesium perchlorate. And this last one, what is Ca? Calcium. And this PO4 is at the bottom of your polyatomic ion sheet.
Phosphate.
Why is it? You're good.
What are you looking for?
So we got calcium, and then what is PO4?
Phosphate.
Phosphate. So what will I name it?
Calcium phosphate.
Calcium phosphate.
What does the two outside of parentheses mean?
So it means this is, each of these is an ion in itself, right? It's got a, we know it's got a negative charge, right?
Yeah.
Calcium has how many, gives up how many electrons? Take a look on your chart. Your periodic table.
Gives up two.
Gives up 2. Well, phosphate has a charge of -1, so I need 2 phosphates
So that's.
to balance that charge, yeah. And same thing here with magnesium and perchlorate, right? So this has a, this takes on a +2. This only has a -1, so I need 2 of them. Okay. Of course, it's opposite up here. If I have 2 sodiums, then what's my charge on my carbonate?
2.
Not positive. This is going to be positive. This has to be negative. Negative what?
-2.
-2. Okay.
And you don't write that outside.
No, yes, no. Okay. Let's do. I don't want to lose you guys. I don't want to leave anybody in the dust. Let's do a little more practice. You wrote out the formula. lithium acetate, potassium nitrate, lithium bromide, magnesium iodide. What's always first here?
The metal.
Always the metal first, right? So those are easy. You can just go look those up. Sodium, what's the symbol for sodium? Na. Good. What's my symbol for potassium?
K,
K. For lithium?
Li,
Li. And for magnesium?
Mg,
Mg. We feeling good about that? Acetate, what's my formula for acetate?
C2H3O2.
C2H3O2. What's the charge on that?
Negative 1.
-1. What's the charge on sodium?
Positive.
Positive 1. So these are good, right? Nitrate. What's my chemical formula for nitrate?
NO3,
NO3. What's my charge?
-1,
-1. What's the charge on potassium?
+1,
+1. So those charges balance. Lithium bromide. What's the char or what's the chemical symbol for bromine?
Br,
Br. How many electrons does bromine want to take? 1. It wants to form a -1 ion. How many does lithium want to give up?
1,
1. It wants to form a +1, right? Cation. So you put these two together, boom, we're good. Magnesium iodide. What's the chemical symbol for iodine? I.
and it would be 2,
And it forms, what's the charge on iodine? Does it want to make a -1 or -2?
-1,
Wants to do -1, but magnesium wants to make a +1 or a +2?
+2,
+2, so how many iodines do I need?
2,
2. So we go MgI2, right? How's everybody doing right now? It feels good? By the time you get a little practice quiz or something like that, or a homework quiz, life will be good? Okay, I like to hear that. Because we have a test, what, in a week? Right? It's got this on it. Okay. By the way, did you catch that? Test on the 11th? Okay, very good. Somebody let Jason know. Okay. All right, what's next? What's next is metals of variable charge.
yes, finally.
You're excited. Metals of variable charge.
So the transition metals,
Yes. So, a friend here made a note that these are the transition metals.
I wasn't sure if we were going to cover that today.
These do tricks. We're not learning all about just yet, but we will later. Okay. What do we want to know about them? Well, take a look at your periodic table that I gave you. It's not doing a very good job. Well, kind
It
of.
shows the charge in the
Yeah.
right.
Take a look at iron. It's group 8. It's at the top. Chemical symbol is Fe. Okay. What charges of ions does it like to make?
+2 and +3.
+2 and +3. So the way that we do this, we use iron as our example, is that we write the name of the metal, and a Roman numeral for the charge. I was so naive. Why did I think I was going to get this done on one board? Okay. So you write the name of the metal and then the Roman numeral for the charge. So let's do iron. I want to do iron +2, okay? So Fe, 2 plus. When I go to write this in nomenclature, it's going to become what?
Iron with parentheses.
It's going to become iron 2. If I had Fe3, that would be iron, and in parentheses 3. This matters a lot. Let me give you an example. Both of these exist in nature. Both iron chloride, right? That's what that looks like. But iron chloride can't be FeCl2 and FeCl3 at the same time. So I need a way of denoting these two, of naming these two. And so what we do, how would I write this? Iron what?
Iron.
First of all, I guess we need to think about chlorine. What charge is chlorine going to take on? Plus or minus?
1.
Plus.
Is iron going to form a positive or negative ion? Look at where it's at on the periodic table. It's a non-metal, right? So it's going to form a cation and negative, right? Okay. And
Anion.
so it's going to be negative 1 or negative 2 or negative 3 or negative what? Look at where it's at. Look at where it's at on your periodic table. It's going to be negative 1. It has 7 valence electrons, so it wants 1 more, right? So chlorine, how many? So I've got 2 chlorines, each carrying an electron. So what is, to balance that charge, what does iron have to be? Plus 2, right? So this will be iron 2 chloride. This one would be iron 3 chloride.
Forgot the L.
Beggars can't be choosers. Let's get some more practice. No blurting on these. You're done. Good for you. Just hang out. Let's do CO. Let's do CO F2. Oh, I'm sorry, F3. Let's do you want to do manganese, you said?
Yes.
Manganese. Let's do one more here. Let's do so what's my trick? What's the first thing I want to do?
Find the charge of the
When I actually name it, what's the first thing I write out?
metal.
The name of the metal, right? So this one's going to be manganese. This one's going to be copper. This one's going to be cobalt. This one's going to be cobalt. Okay. Now, the next thing I need to do is because these are metals of variable charges, I need to have some parentheses. Let's put my Roman numeral in, right? Figure out what Roman numeral in a minute. Then I name this anion, right? So what's the name of the OH anion? Hydroxide. So this is manganese something hydroxide. And this is copper something what? Bromide. Okay. And this is cobalt something, this would be oxide. And this would be copper something fluoride. Now all I've got to do is figure out my charges. What's the charge on a hydroxide? -1. Since I have 3 of them, what does my charge on my manganese have to be? It has to be +3. What's the charge on bromine? -1. So what does my charge on copper have to be? +1. I got to put a 1 right here. Okay. Charge on oxygen
-2.
would be a -2. And so on a copper, or cobalt, I'm sorry, it's got to be 2, right? Fluorine, -1. So my cobalt has to be +3. Who's still in the weeds? Just an honest hand.
Who what?
Who's still in the weeds? Who needs more practice?
I'll go.
Let's do 2 more and we'll move on. Okay. Let's do cobalt again. What are my possible oxidation states for cobalt? You see where it's at? Where's cobalt? What's its atomic number? 27. So find it on there, atomic number 27. And on the top right, it says plus something, and below that it says plus something else. So what are the 2 states there? +2 or +3? Okay. Do you want to do a +2 or do you want to do a +3? Let's do a 2. Okay, so cobalt with, let's do fluorine. Okay, what's the charge on fluorine? Or fluoride? It's going to be a -1. Look at where it's at on there, right? So it's right there, so that those always want to pick up 1 more electron, right? So since I've got 2 of them, that's a total of -2. It's got to be balanced by a +2.
Okay.
So this has to be cobalt 2 fluoride, right? And this is still fluorine or fluoride, right? So it's going to be -1 each one, but I got 3 of them. So it's going to be cobalt what fluoride?
3.
How many negative charges will I have here? I need 3. So how many, what does my charge be here? How many? 3. Positive 3, right? So this will be cobalt 3 fluoride. Right. I want to encourage you to go read the book, work through it. It gives you some problems as well, okay, and some solutions. So work through those. That'll give you the extra that you need. Okay. Next is going to be ionic hydrates. These are not complicated. That's a good thing. We don't have a ton of time. I'm going to write them over here because I'm out of room over there. Okay, ionic hydrates. Spell it here. So here's what's happening. You're looking at an ionic compound that when it forms, it's a salt. When it crystallizes, it is trapping water, or water is somehow involved in the formation of that crystal. So I'm gonna just kind of define this to you. So it's an ionic salt, which I guess all salts are, with water in the crystal structure. Let me write that down, and I'm going to explain why this matters. Where did we get salt from? Like table salt, where do we get it from? The sodium chloride, but literally where do I get it from? Okay, where the story get it from? Like where will I find tons of this?
The ocean.
In the ocean, right? It's in what we call a solution. We haven't talked about solutions yet. But a solution is the idea of something, it's a solute dissolved in a solvent. And we haven't used those two words yet, I know, but in the case of the ocean, your solute is the sodium and the chlorine and the other little things that are in there, and then the solvent is water, okay? And so you have a solution. You have an ionic compound in a solution. Well, if I get rid of the water, what am I left with? The salt, right? And it forms what we call a crystal, right? And we mine salt, right? Like all the Himalayan, the cool pink Himalayan sea salt everybody likes. That, we think was once salt water. It's pink because it had some iron and stuff in it. And then the water went away, and what was left was the salt, okay? And so you can do this with any of these ionic compounds, is you drive away whatever solvent they're in, and you're left with just the solute, and it forms a crystal, right? And so it's a salt. Well, sometimes certain molecules, when they're forming their salts, water is not just the solvent that it's all around, but it's actually in the crystal structure. Does that make sense? Okay, and so this is what we're talking about here. Ionic hydrates are salts with water in the crystalline structure itself, like it's an integral part of it. If you took the water away, the crystal wouldn't work the same way. So there's practical things to this. One is you could heat these guys up and you can drive the water out. But when you do, the crystal changes shape. And so some of these do like color changes and stuff like that because you're having changes to its chemical structure. How do we name these? So what we do is we give the name of the ionic compound. So I'm going to write that in one color. So name of the ionic compound. Okay. Plus a Greek prefix that corresponds to the number of water molecules, but I'm going to write hydrates, okay? Just so you know that that's how this is. We don't go, oh, it's, well, let me give you an example here. We don't say, oh, it's copper 2 sulfate pentawater. We say it's copper 2 sulfate pentahydrate. So we're going to say hydrates for the number of waters. We'll do a couple of these here in a minute, okay? This is how you name it. So, you give it at least 2 examples here. How do I name this?
Copper.
Cu is copper, right? So I write copper. The charge on sulfate is
-2.
-2. So my copper has to be with a charge of 2, right?
Yeah.
So copper 2 sulfate. How many waters do I have? 5, so that's penta. Hydrate. So that's how you name that. Copper 2 sulfate pentahydrate.
That's a mouthful.
It is. Let's do another one. So what is this?
Sodium.
Sodium. What is this? CO3. Take a look at your polyatomic ion sheet.
Carbonate.
Find carbonate on there. Find its charge.
-2.
Yeah, and you probably know that just from looking at this, right? Because you know sodium has a +1, charge is out of balance. So, okay, so this is sodium carbonate.
Decahydrate.
Deca, it's our prefix, decahydrate. Would you like an easier one or two of these? If it's easy for you, don't answer, okay? How would I name that one?
Question,
Yes, sir.
is 10 deca in Greek?
Yes, it is.
Okay, so we've got to learn the Greek numbers.
If you, on your test, if you don't know that one, just raise your hand and go, hey, what's the
Okay.
Greek prefix for 7? And I'll tell you, it's hecta.
Yeah,
Okay. All right. What's this? NaCl. Sodium
okay.
chloride. Greek prefix for 2 is dihydrate. So this would be sodium chloride dihydrate, right? I could do LiBr. What would this be? What's Li? Lithium, bromide, pentahydrate. Lithium bromide pentahydrate. You want one more? No? Everybody's good? Okay, good. Because I got more to do. All right.
Well, we're 2 minutes late.
Are we over time?
What?
Are we over time?
Yeah, we're over time.
All right.
Also,
Well,
I have
We'll pick
another-
up there next time.
The only reason I said anything is because I have another thing I have to get to in 8 minutes.
All right. Well, the Lord bless you and keep you. Cause His face to shine upon you. I should give an extra credit point if you can tell me where that's from in the Bible.
Oh, say it again. What-
The Lord bless you and keep you and cause His face to shine upon you.
Never mind.
You can look it up. I mean, literally, you can Google what I just said.
See you.
God bless, guys. Have a great day.
Thank you.
Yeah.
Just
know I messed up on one of them like that.
I think that first one we took was like 3.
Yeah, so,
And the next one was 4, and there was 2 answers for 4, and I think I just chose the wrong one.
okay, let me have a second here, so I don't forget to do this. Try to leave it clean for whoever's next.
Yes, sir.